Hello, my name is Ali, and in this section we will be exploring how concepts we learned about in class, such as the law of electromagnetic induction, aka Faraday's law, and time-varying fields, are utilized to make maglev train systems. Maglev just stands for magnetically levitating. Just a little background information before we start. The magnets used in maglev train cars are superconducting magnets. This means they are electromagnets that are cooled to roughly negative 267.8 degrees Celsius, whereas absolute zero is negative 273.15 degrees Celsius. This is a difference of 5.35 degrees only, roughly. And keep in mind that absolute zero is the theoretical coldest possible temperature where even atoms will stop vibrating. This just goes to show you how cold the magnets have to be. Now, the reason they have to be this cold is because this process dramatically increases the electromagnetic power. Now, let's talk about three things every high-speed train needs. Number one, propulsion. The magnetic fields generated from the superconducting magnets interact with simple metal coils made from good conductors like aluminum, and by passing them, they create a current inside the coils, which subsequently makes another magnetic field. So, maglev trains use electromotive force to propel themselves. And we know that the law of electromagnetic induction is whenever a conductor is placed in a varying magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called the induced current. Now, looking at our explanation, we talk about magnetic fields from the train car passing the coils. This counts as the varying magnetic field because the magnetic field will be getting weaker as the train moves further from the coils. And the induced current is also mentioned in our explanation. By alternating the current power supply to the coils, we can utilize magnetic attraction and repulsion to move the train car along the guideway. The frequency of this switching is used to control the speed. This relates to time-varying fields since the magnetic fields are constantly changing. And if you think about it, they have to be, because if the magnetic fields were constant, the system would just stay at equilibrium, the train wouldn't go anywhere. Number two, lift. Using the same magnetic polarity on the ground as the bottom of the train, they can magnetically levitate the train to get a closed, frictionless environment, which allows these trains their great speeds. Recall that air resistance will still be there and cause some friction, but you won't have to worry about any of that ground friction. And the train is kept at an optimal height using magnetic repulsion from the coils embedded in the ground, and this optimal height varies between train to train. Now, this concept is the same concept as trying to push two magnetic poles together. Only the magnets in this case are so strong that they can cause serious trouble for people who have pacemakers. But don't worry, the train cars are insulated to the strong magnetic fields from the superconducting magnets, so the passengers are safe. And the third thing that every high-speed train needs is guidance slash steering. Now, the train achieves lateral stability by having the guideway imbued with coils that have currents flowing through them, and when the train steers off center, the electromagnets they use magnetic repulsion to keep the train car in the optimal place. Now, this is the same concept. It's a similar concept as lift, except in this case, where it's horizontal and the electromagnetic repulsion is happening from both sides as opposed to only one. And this is because we want to have the train always in the middle of the guideway. We don't want it to steer off center. That can cause problems. We don't want it to go off the track. And as you can see in this photo, you can see the coils on the sides, you can see the magnets on the bottom. Now, to summarize the analysis, We talked about maglev technology, and we talked about how crucial the law of electromagnetic induction, aka Faraday's law, and time-varying fields are to it. And we have extensively covered both those topics in class. And I'd just like to end this off by a quote from Jesse Powell. A maglev train car is just a box with magnets on the four corners. This is an oversimplification, but it's also not wrong. The train car is just a fancy box with fancy magnets that are cooled to a certain temperature and all that. However, maglev technology is not just about the train car. And I hope by exploring propulsion, lift, and guidance with me, you were able to see just how crucial the guideway is in maglev systems, how big of a role it plays. It is just as important as the actual train car, and they are two halves to a whole. Thank you.